Okay. So I'm just redoing the last part again, because this is actually this is from example 2.19. I didn't realize to calculate the time again. I would have done it earlier, but let's do it to show you what the quadratic formula is, to get everybody up to speed. If you've never seen it, now there's no excuse. All right, so this formula over here looks like the quadratic equation, right? If you remember, right, x plus, or a plus b x plus c is equal to 0, right? And if we call this position y0, 0, when it comes back down, this is 0, right? So this is 0, and then we match it up. If you look at our variable here is the time, so that's like our x. We relate it to our x. This is the general formula. Let me write it. Right, so this is the general quadratic formula. Fatty, the meeting ends every 40 minutes. You have to rejoin. It does it for all of us. I haven't heard back from Zoom about getting a pro account, so I'll have to follow up with that. But anyway, so this is the general quadratic formula, and if we look, our equation falls into that, right? Instead of t, we in this case, t is our variable, or x, and then we have a, b, c. It's written backwards over here than compared to here, but it's the same formula, right? So this is 0, so we could use our quadratic formula over here, and then we know y0 is 0 at that position because we set it equal to 0. This is 15t plus 1/2. I'll put the minus sign outside. 1/2 9.8t, right? And from high school algebra, we know that x has a solution, well, two solutions in this case, minus b plus or minus the square root of b squared minus 4ac, and this is all over 2a. So this is the general formula to solve a quadratic equation, right? And in this case, now we relate what these constants are. In this case, b is 15, a is minus 1/2 9.8, so 4.9, right? And c is 0, right? So let me write it out. A is equal to minus 4.9, b is 15, and c is 0. Now we use the quadratic equation. So then we solve for t. And so we get minus 15 plus or minus the square root of 15. This is 0, of course, because c is 0. And then over to a, and minus 4.9. Right? And if you look, there's two solutions. Right? So the two solutions are .96 when we actually solve it. Or I'm sorry. The two solutions are, we're measuring when it comes back down, right? The two solutions are, if you look, 15 squared, the square root of 15. So this will give us plus or minus 15 over. So we get two solutions when it gets to this point, right? If you look at over here, right? When these two 15s add up and then when they subtract. Does this make sense? It does, right? So T is either equal to 0 or 3.08. Sorry. I missed the negative sign over here. So we get two solutions, 0 and 3.08. This makes sense, right? Because there's 2 points that this ball is when it reaches over here. Well, in the beginning, right as we throw it up, it's at y is equal to 0. So then that's t is equal to 0. And then again at 3.08, right, when it reaches the bottom position. That's true for any of these positions. So in the book, in 19, they actually put a position after 8 seconds, or at 8 meters. So when it's at 8 meters, at what time does it reach that position? And we just plug in 8 meters over here, and then we can solve for it, and we get two positions. One when it approaches it going up, and the other time when it comes back down. So that's why there's two solutions here, and it makes sense in this problem. So both solutions are actually physically viable in this problem. Any questions on these problems? Okay, let's move on. I'll talk about how we use integrals in this for this stuff. So far we've done derivatives, but we use derivatives to go from x to from position to velocity, and from velocity to acceleration. But from your calculus class, an integral is the antiderivative, and so that means that now we could go from acceleration to velocity, and then velocity to position. So let's start off with acceleration. So acceleration is just the change in v over the change in t. So then we have this dv is equal to at, right? Now we do the integral. We could do an integral now to get rid of everything. So let's do that. We integrate across dv on this side, and then we integrate on this side. Whatever we do on this side of the equation line, we have to do on that side. So we have to integrate it. And we'll go from v naught to some vt later, right? We'll just call it t. I don't want to put in type it in as a function yet, because it's easily confused as multiplied by t, but that's just a function. I'm just saying that v is a function of t. So we go from the beginning velocity to whatever ending velocity, and then here we'll say that t is equal to 0 at the beginning, and then to some t later, right? So then we integrate it. So we integrate each side now separately. So here we'll have v, right, from v naught to v, and then here is this dt, so it's a times t. A is just a variable. I mean, it's just a constant like we've been dealing with. So from 0 to some t later, right? And we plug it in. Now it can get a little confusing because over here t is the variable, and then this t we call t later. So like we plug in another variable. So just be cognizant of it. It's just that we're plugging this into here to show that, to be general, that it's just sometime t later, right? So then we plug it in, and we get v naught is equal to t minus 0. Of course, that cancels out, and we can solve for v, and we get the formula that we had before, right? And this is assuming that a is a constant. So a is a constant here. So we have v. We got to our formula. Now let's go from v to the position. So now we have this. The position. How we relate v to the position is that the change in position over the change in time is equal to v. Right. Then now we do the same procedure. Right. We have x naught to x dx, and we bring t over to the other side, right? Right, and this is dt. Now here, v is not a constant. We don't assume that v is a constant, and it's dependent on t. Because it's dependent on t, we're integrating in terms of t, we have to express v as a function of t to solve this. So where's our function of t? It comes from over here. So now we plug that in, and then of course the limits are from v naught to v. So then now we replace v as the function we just derived, and we have this. Right? And now we can solve. Right? So this is dx x minus x naught, as we did up here. I'm skipping that step, and then now we have it from, so we got to change our variables. So from 0 to t, right? So on this side, let's write it out first. So when we integrate it, we get v naught t plus, we already have a t, so we do the opposite as the derivative. There's a section in the back of the book that talks about how to do integrals. Just check that out. But for the power law, you raise the power now. You do the opposite operation as the derivative. So this is to the second power. And then with that new power, you divide it by 1/2. See that? And the reason to do this is now that when we take this derivative, we end up back with the same quantity that we had in the integrand over here. So we have this now, and we have this go from 0 to t. Of course, 0 is this whole side, and we end up with x. I'm bringing x naught over to the other side, plus v naught t plus 1/2 at squared. We get the same exact quantity that I showed you, that we derived it earlier using the average velocity, that average velocity equation. All right, but here we did it fully using calculus, and this is the correct method to do it. And we could use calculus. So now we could do stuff that where the acceleration can change over time. One example of this is if there's wind resistance. So wind resistance depends on its velocity. If its velocity is changing, so is the resistance, and then therefore the acceleration. So there's a lot of situations where, well, most situations the acceleration is not constant, right? A rocket, a car accelerating. Remember last time how we estimated how fast the car goes, how fast the cop car takes to catch up to the speeder, and it didn't work out very well. That's because we assumed the constant acceleration when that's not the case. But with calculus, now we can do something like that. So let's say if our acceleration depends on t in some way. So let's say our acceleration is given to us as 7t, right? And the 7 has units of meters over seconds cubed, right? Because we need to end up with meters over t squared. So so the units will work out in the end. So let's assume that. Let's figure out what our velocity would be as a function of time in this case. So we'll go back. Let me erase this. So let's figure out what the velocity is if we don't have a constant acceleration. So given let's find v as a function of t. So now, so let's do that. We'll start off with this formula, right? Same formula, right? It's just the acceleration is just a derivative. Now we can replace a as 7t. And then we just do the same procedure as before. V is equal, all right, we'll set up the integrand from v naught to v, and then here from 0 to t. And let me just make the case that t is equal to 0 over here, and v is equal to 0, so that you know this is just the starting position. It doesn't have to be 0. And then we have 7a dt, or 7t dt. And now we do it, this integral. All right, we got v minus v naught. And then we'll have just 1/2 7t squared, right? And then since this is 0, the beginning point is 0, so that we're just left with this. And then we find that v naught is equal to this. I didn't simplify it just so that you can keep the expression. No. So now we can handle non-uniform acceleration, right? You just got to do the integral and figure out the formula. And then we can integrate this again and get the position, and then we'll have a new set of equations. And then to finish up this chapter 2, 2.9, I normally would do this in more detail, but this is a summer course and we should move on to more stuff given the time constraints. But let's talk about it briefly. So in a graph, right? So let's say if we had a graph of velocity over time. We have something that's accelerating at a constant rate, right? We know that the slope is the acceleration is a, right? In this graph, you know, how fast does this graph increase as we move along in t? That's acceleration, right? We know that, right? But how can we represent position in this velocity graph? Anybody?
It's going to be the integral.
Yes, it's going to be the integral, right? What does the integral represent? That's the big question.
Area under the curve.
The area under the curve,
yeah.
Right? So this is the integral. This whole over here, right? Up until this point, wherever we do it. So if we calculate the area underneath this curve, this represents the position or how far I traveled, right? So, and all that the integral is doing is it's adding up this length at each point. Let me use a different color. So all the integral is doing is adding up, and so it's measuring the velocity at each point, and it's adding it all up into one quantity. So if I measured the velocity at each one of these points, now since we're doing calculus, these points would be infinitesimally small, and I added up all these points, we would have the position, right? And if you think about it, that's exactly what position is, right? So the velocity.
When I was about 13 years old, my mother lived in the basement. She worked at McDonald's, made $50 a week. We ate Big Mac and fucking French fries every day for years. Where I'm at in my career right now is surpassed my dream. My dream was to get a job at McDonald's to send $50 a month.
Hey Ash, you really have to stop doing that. If this keeps happening, I'm gonna have to ask you not to be present, okay? And I'll have to report it immediately. You can't. This cannot happen again. You understand? Okay. I'm not gonna stand for that. All right. This is a college course. Anyway. So if we add up all these positions, we'll get the position. And if you think about it, this makes perfect sense with the definition of velocity as compared to position. Now, if we don't explicitly know the function, a lot of times these functions are too hard to calculate. Like, let's say if we're in a car and we're accelerating and deaccelerating, whether at a certain rate, whether due to traffic or whatnot, the graph could be pretty complicated, right? You know, it could look, your velocity could look something like, oh, not that. You know, it could look something like that, your velocity, right? How do you integrate that curve? You could spend all day figuring out an equation for this, or you could approximate. You can approximate it. So the way to approximate integrals is that instead of measuring the velocity at each point, you add it up. What you do is at each of these positions, you take the average velocity. So between this point and this line, I just take the average velocity, and then I would just take the average velocity. Let me write this in you take the average velocity and you multiply it by the width over here, right? So that now we can approximate this function, right? And then over here we do the same thing. Right, and so on and so forth to the top. And these can be very good approximations. If you look, you kind of miss a little bit of, you kind of add on a little bit of the bar over here, and then you miss part of the area over here, but it's a pretty reasonable approximation, right? If you look at this one, you can see this better, right? You have an extra area over here, but somewhat subtracted to this position over here. It's an approximation. And the smaller these bars get, the better it is. And if they get infinitesimally small, they become equal to the curve, and then you get an integral. But now you can add up all these velocities at each point, and then this is an approximation of the integral. So if this is V naught, and this is sometime later, we can summarize this as V from each position, and this is equal to the summation of each one of these boxes to T2, or I'm using a different right? And we have a summation over here. So we add up, and all this is saying is that we add up the average velocity times this delta t at each one of these positions. Right? And then you can approximate it and go that way. Okay. That will finish chapter 2. Let me think. Let's stop right here and come back in 10 minutes, and then we'll begin chapter 3. Sure. So I'll see you guys in 10 minutes.